Welcome to Maths with EJD. We continue with power series as we talk about Taylor and Maclaurin series, two very important series that can help us get polynomial-like expressions for any kind of function at all, even the ones that are known not to be polynomial in nature. Okay, so first off, the Taylor series is an infinite series that represents a function. It represents a function as a sum of its derivatives, the sum of its derivatives at a single point. So this is talking about the Taylor series to start with. Okay, now the series is centered around a particular point. It's centered around a particular point, usually denoted as A. Okay, so that takes us to the idea of Maclaurin series because they are really close. Maclaurin series. Okay, the Maclaurin series, on the other hand, the Maclaurin series is a special case of the Taylor series, where the series is centered around A is equal to 0. That's the Maclaurin series. So Maclaurin series is more like a simplified version of the Taylor series because it is now done at A equals 0. Okay. Now let's see the expression. Okay. Expression of Taylor series. This is how that looks. The Taylor series is a function f of x centered at x equals A. The Taylor series is a function f of x. Oh, okay. That is not proper. The Taylor series of a function, the Taylor series of a function f of x centered at x equals A is given by f of x equals f of A. That means whatever the function is evaluated at the given A plus f prime of A multiplied by x minus A plus second derivative of the function x evaluated at A divided by 2 factorial multiplied by x minus A all squared. Okay. That's disappeared for a moment, but we have it back. So plus the third derivative, f prime prime, that's the third derivative of evaluated at A rather, divided by f factorial, multiplied by x minus A raised power 3. All right. Plus, the nth derivative evaluated at A all over n factorial multiplied by x minus A raised by n. Now you can see it still looks like the typical power series, with x minus A, except the only thing is that A in this case is the center, x is the variable, and then you can say the other part is the coefficient. All this part is like the coefficient. And of course, it doesn't stop at 10, so it keeps going. It's an infinite series, so it has no end actually. So this is what the Taylor series is about. So you can see that here, Fn of A is the nth derivative. It is the nth derivative, whatever n is, maybe second derivative, third, fourth, fifth, and so on, is the nth derivative of f of x evaluated at x equals a. That's the first thing. Then secondly, the term x minus a raised to power n indicates the distance. It indicates the distance from the center A, the distance from the center A. Okay, so clearly A is the center. So let's take an example of, let's take some examples. So let's take at least one. Let's see how that works. Okay, so we have example. So we have this, and so say find the Taylor series expansion, for e raised to power x around x equals 1. So the center is 1 now, and the function is e raised to power x, the exponential function. So what's the first thing we do? First step, let me write that as step. Let me say step 1. So for step 1, what do? You find the derivative, find the derivatives of e raised to power x. That's step 1. Find the derivatives of e raised to power x. Of course, f of x is e raised to power x. So the function you're dealing with is e raised to power x. So if you differentiate that, f prime of x, first derivative, it's e raised to power x. Second derivative is also e raised to power x. So this is one function that remains the same forever. Third derivative is also e raised to power x. And it goes on and on. It's still the same e raised to power x. So that's the first step. Find the derivatives of e raised to power x. So the next thing is evaluate the derivatives at x equals 1. Step 2, the center is 1 that we are given. Step 2, evaluate the derivatives. Evaluate the derivatives at x equals 1. Okay? At x equals 1. So of course you already know that f of x is e raised to power x. So it means that f of 1 is e raised to power 1, which is simply e. Okay? Then f prime prime, second derivative of 1. Of course, second derivative, sorry, that should be first derivative. First derivative, f prime of x is e raised to power x. So f prime of 1 is also e raised to power 1, which is e. Then f prime prime of 1 is also e raised to power 1, which is e, because second derivative is also raised to power x, so you have e raised to power 1. And third derivative, f prime prime of 1 is also e raised to power 1, and that is e. So it's like the same all the way. Okay? So step 3 now, we've got e all the way. Step 3 is to plug into the Taylor series formula, So if you plug that into the Taylor series formula, then you see that e raised to power x is actually e plus e into x minus 1 plus e. Should I really write that again? So remember, okay, I think I should write that for the sake of emphasis, right? So don't forget that for Taylor series, the Taylor series expansion for any function f of x is given as f of a plus f prime. So around center A now, f prime of a, into x minus a, right? That's this f prime of a into x minus a, and then we continue like that, plus f prime prime of a, all over 2 factorial x minus a squared, okay, plus f prime 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 of a all over 3 factorial x minus a raised to power 3. And that goes on forever, okay? That goes on forever. So if you are applying this in this case, so that's, we're dealing with f of 1. We can say that f of x actually, which is e raised to power x here, is f of a, which is f of 1 in our case. So f of 1 is e, plus f prime of a is also e into x minus 1, plus again f prime prime of a is actually e over 2 factorial into x minus 1 squared, plus again e over 3 factorial, then x minus 1 cube, plus every other thing that follows. So that is what we expect for e raised to power x for Taylor series centered around 1. So we can say this expansion gives the Taylor series. So this expansion gives the Taylor series for e raised to power x centered at x equals 1. So that's for Taylor series. That's expression of Taylor series. Now let's take the expression of Maclaurin series. Expression of Maclaurin series. So we know Maclaurin series is Taylor series, except that the center is 1, except that the center is 0, sorry. So Maclaurin series is Taylor series with center 0. That's basically the idea. So the Maclaurin series is a special case of the Taylor series, centered at x equals 0. Okay, the formula is, as you can already expect, anywhere you have a, 0 takes over. So you have f of x equals f of 0 plus f prime of 0 x. The center is 0, so x minus a is still x minus 0, so it's still x. Then you have f prime prime of 0 all over 2 factorial x squared plus f prime 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 of 0 all over 3 factorial x cube, okay, plus it goes on, and you can talk about fn of 0 over n factorial x raised to power n, and it goes on forever. It's an infinite series. So let's talk about, what we just did is e raised to power x, right? So let's talk about Maclaurin series for e raised to power x. That's as an example. So again, let's take an example with e raised to power example. Find the Maclaurin series. Find the Maclaurin series for e raised to power x. Now we don't have to talk about the center because we already know that the center is 0 for Maclaurin series. So again, we have to do the normal thing. So first step, find derivatives. That is step 1. So that means that f of x is e raised to power x. F prime of x is also e raised to power x. F prime prime of x is still e raised to power x. And f prime 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 of x is also e raised to power x. So that goes. And the next thing is step 2. Step 2, evaluate the derivatives at x equals 0. Evaluate derivatives at x equals 0. That's the next thing. So here now, f of x is e raised by x. So f of 0 would be e raised by 0, which is 1. Then f prime of x is also f prime of 0. That's e raised by 0, which is also 1. Okay, then we have f prime prime of x, f prime prime of 0, right? Which is also e raised by 0, and that is still 1. Then lastly, we have f prime 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 of 0, which is still e raised by 0, and the answer is 1. So with that now, we have all that. So we can restate the expression, that we have done step 2. This is step 1. This is step 1. So step 2 now. So we have done step 2. So step 3, plug into Maclaurin series formula. Maclaurin series formula, which we know already to be f of x, which is equal to f of 0 plus f prime of 0x plus f prime prime of 0 over 2 factorial x squared plus f prime 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 of 0 over 3 factorial x cubed, and so on and so forth. So with this now, we can say therefore that f of x is e raised power x, which is equal to f of 0. We know everything is 1. F of 0 is 1. All the f of whatever is 1. So we have 1 plus 1x plus 1 over 2 factorial x squared plus 1 over 3 factorial, f prime prime of 0 is also 1, x cubed, and it goes on and on. So we can say, therefore, e raised power x is equal to 1 plus x squared. Oh, I guess I was too fast to render that correctly. 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x4 over 4 factorial plus all that. And that is why the exponential function is expressed this way. So if you're wondering how e raised by x is 1 plus x and all that, so you can see it is the Taylor Maclaurin expansion for e raised by x that gives us this popular expression for Maclaurin series. Okay. All right. So I mean, it is obvious that the Maclaurin series is way easier than the Taylor series. So let's take one or two examples and see how we can get the series for other expressions. For instance, let's do sine x, cos x, and log 1 plus x. Before we go, I'll just focus on only the Taylor series. So let me just say more Taylor series examples. No, more Maclaurin series examples, because Maclaurin is simpler. Should I do that? Okay, you know what? So I'll do Maclaurin. I'll do Taylor and Maclaurin for sine x. Then I'll do only Maclaurin for cos x and log 1 plus x. Let's do it that way. So let me say further examples. So I have Taylor series for sine x. Taylor series for sine x. So I'll just go. I won't worry about all these steps again. So I mean, I'll do the step, but I won't have to state step 1, step 2. So first, find all the derivatives. So you have f of x equals sine x. Okay, let me do this. Taylor series for sine x. Around x equals pi over, let's say pi over 6. That's 30 degrees. Pi over 6 rad. So that means we have sine x, right? We have sine x. That is our f of x. F of x is sine x. Okay. F of x is equal to sine x. So now that f of x is sine x, right? F prime of x is cos x. When you differentiate sine x, you get cos x. F prime prime of x, that's differentiate cos x, now you have minus sine x. Then f prime 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 of x now, differentiate sine x, you get cos x. So it means differentiate minus sine x, you get minus cos x. Well, maybe we can take it to the fourth. 1, 2, 3, 4. The fifth one is the fourth derivative. Differentiate cos x, you get minus sine x times minus, that's sine x back. So in that, and then of course, if you like, you can even take it to the fifth derivative. Differentiate sine x, now you're back at the cos x we started with. So those are the derivatives now. Derivatives. Then let's talk about the evaluations. Evaluations at x equals pi over 3. Pi over 3 is pi is 180. 180 over 3 is okay. Did I say pi over 3? It's pi over 6. Pi over 6. So that's 180 over 6. That's 30 degrees. So let's evaluate. So for this now, we have f prime of pi over 6. That is like cos pi over 6. Cos pi over 6 is cos 30 degrees. Do I remember what that is? Is it root 3 over 2? I remember sine 30. Sine 30 is 0.5. So cos 60 is 0.5. Okay. What do I do now? I'm trying to get, I think it has a very simple expression. Is it root 3 over 2? I want to believe it's root 3 over 2. Sine 60, okay, let me do a quick evaluation. So cos pi over 6. I want to be very sure so I don't make a mistake. Yeah, so cos pi over 6 is root 3 over 2. Yeah, root 3 over 2. So it's root 3 over 2. Okay, so here we have f prime prime of pi over 6. That is minus sine 30, minus sine pi over 6, which is 1 over 2, easy. And then we have f prime 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 of pi over 6. That is minus cos pi over 6. That is minus root 3 over 2. Then we have f iv of pi over 6. That's the fourth derivative. That is sine pi over 6. Sine pi over 6 is simply 1 over 2. And lastly, we have fv of x. fv of pi over 6. fv of pi over 6. And that is cos pi over 6, which is again root 3 over 2. So now we plug into the formula, plug into the Taylor series formula, And the Taylor series formula, once again, is f of x equals f of a. Our a here is pi over 6, f of a, that's f prime of a, x minus a, then f prime prime of a over 2 factorial, x minus a raised to power 2 plus f prime 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 of a over 3 factorial, x minus a raised to power 3. So we went up to the fifth. So we have fiv of a over 4 factorial, x minus a raised to power 4, then plus fv of a over 5 factorial, x minus a raised to power 5, and so on and so forth. So let's put all this. So we have f of x now, which is sine x, right? Sine x. So that is sine x, and that is equal to f of a. F of a is the first one. Oh, okay, I forgot to do the sine x. So f of pi over 6, that is sine pi over 6, which is actually 1 over 2. I forgot to do that. So f of a is 1 over 2. Then f prime of a is root 3 over 2. Root 3 over 2, x minus, our a is pi over 6, plus f prime prime of a. F prime prime of a is, so this is minus now. This is actually minus. So differentiate cos, you get minus. So f prime of a is minus 1 over 2. So that is minus 1 over 2 minus 1 over 2 into x minus pi over 6 raised to power 2. Then f prime prime prime, that's third derivative, which is minus root 3 over 2. So you see that's minus root 3 over 2 x minus pi over 6 raised to power 3, then that's minus root 3. Then fiv, that's the fourth derivative. Again, we're back to half. So 1 over 2 x minus pi over 6 raised to power 4. And lastly, fifth derivative plus root 3 over 2 x minus pi over 6 raised to power 5, and so on and so forth. So that's actually the Taylor series for sine x. So I'll do the same for for Maclaurin series. So maybe I won't go all this far. Okay, well, I can still do the same, right? So now we want to find the Maclaurin series, find the Maclaurin series for sine x, okay? For sine x. So we already know that is about x equals 0. That's the center is x equals 0. So again, we have f of x equals sine x. So f of x equals sine x. F prime of x equals cos x. And then we have f prime prime of x equals minus sine x. Then f prime 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 of x is minus cos x. I'll stop at the fourth derivative here. Fourth derivative of x is differentiate cos x against sine x. So that's you get minus sine x. So that goes back to sine x. So if you evaluate at 0 now, so f of 0, sine 0 is 0, then f prime of 0. Okay. I guess I'm being too fast now. Okay, so this is sine 0, which is 0. And here we have cos 0, which is 1. We have f prime prime of 0, which is minus sine 0, which is also 0. Then here we have f prime 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 of 0, which is minus cos 0. That's minus cos 0, and that is minus 1. And here we have fiv of 0, which is sine 0, and that is also 0. Okay, let's go to fifth derivative. I guess that will help us a bit more because we are getting so many zeros. Okay, so we have fvx. The fifth derivative of x is differentiate sine x again, you get cos x. So if you evaluate that, that's fv of 0, fv of 0, and that is cos 0 again, which is 1. Okay, so now you understand why sine is an even function. You can already see that here. So you see that for every even derivative, the value is, yeah, is it for every even derivative? Yeah, for every even derivative. So this is 2. For every even derivative, it is actually 0. Okay, so we can plug things in now. We can plug it in. So again, you say f of x for Maclaurin is f of 0 plus f prime of 0 x, all right, plus f prime prime of 0 all over 2 factorial x squared plus f prime 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 of 0 all over 3 factorial x cube. Okay, then I guess I need to shrink this so we can accommodate everything. Okay, plus f iv of 0 over 4 factorial x raised to power 4 plus fv of 0 over 5 factorial plus all that. So let's plug these values in. So we have f of x now, which is equal to sine x. which is equal to sine x, is equal to f of 0. F of 0, you can see that is 0. That's 0. F prime of 0, that is 1. So that is 1 multiplied by x plus f prime prime of 0. F prime prime of 0 again is 0 x squared all over 2 factorial. Then, I mean, okay, that's why you see sine is an odd function, rather. Sine is an odd function. Okay, so it's only odd values, odd derivatives that give you answer, something like that. Then f prime prime, that's third derivative, is now minus 1 x cubed over 3 factorial. Then the next one, the fourth derivative is 0. So for even derivatives, you have 0. So this over 4 factorial. Then the fifth derivative now is 1. So you have 1. So this should be x raised to power 5 right here. So x raised to power 5 over 5 factorial plus everything else continues like that. Okay. So you now have, so you can say therefore sine x is equal to 1x, which is x. This is gone. All the zeros gone. So 1x, the next one is x cubed over 3 factorial, then plus x5 over 5 factorial. So if you want to stretch that further, so that means you have minus x7 over 7 factorial plus x9 over 9 factorial, and so on and so forth. So at this point, you can use this method to for the rest. So I think I don't want to go into other examples because this is getting too long already. So we can take the rest as practice questions. So the first question will be, find the Taylor expansion. Find the Taylor expansion for a f of x equals cos x. You know, we've done sine x. About x equals pi over 6 again. Then b, f of x equals log 1 plus x. About x equals what can we take? So let's say x equals 1 also, you know, x equals 1. Yes, let's do that. Is that going to make sense? That'll be log 2. Okay, so let's say x equals 1 for that. Then question 2, find the Maclaurin series. Find the Maclaurin. So whether I say expansion or series, never mind, it's the same. Find the Maclaurin series for, you know, I don't have to say x equals anything because we just know x is 0. For f of x equals cos x, and b, f of x equals log 1 plus x. So in the next video, I'm going to give the Taylor expansion or Maclaurin expansion for some kinds of functions. So watch out for that. So if you have followed up to this point, I must say thank you for always coming along. If you have not subscribed already, be sure to do that. And of course, hit the notification bell so you can always get alerted when a new video is released. Of course, be sure to comment, like, and share so that more people can be part of this learning process. Thanks for always stopping by. See you next time. Bye.